Centripetal force in action. Today I'm going to go over a few problems. Previously I introduced centripetal force. I told you centripetal force has two main alternatives, mv squared over r and the other formula mr omega squared. M is the mass of the object, r is the radius of the circle, v is the speed, omega angular speed. But more than that, I told you Fc is a role and you have to find a force accepting the responsibility of taking that role. This is exactly what we are going to do today. Moving in a horizontal circle, the first type of problems. When the object is moving on a horizontal circle, basically Fc is horizontal, but mg is downward. So these type of problems are the ones in which mg cannot be directly effective on Fc, but indirectly it might be effective. Let's consider this case, you will learn it. There is a cyclist or a car in a roundabout at a speed of v, and so I may use one of these alternatives. But the main problem is here. How can we find the force taking the responsibility of Fc here? There must be necessarily a centripetal force, but which force is accepting the responsibility of taking that role? Yes, your guess is correct. It's gonna be friction. But which type of friction? Static or dynamic? Guess what? Okay, let me explain it in detail. Actually, you can consider the wheel of the car or the wheel of the bicycle and you will learn it immediately which friction is suitable here, static or dynamic. When the wheel is rolling on the ground, the bottom of the wheel is at rest relative to ground. So it's not sliding on the ground. So it's not going to be the kinetic friction. We always prefer to use static friction. So let's substitute that for static friction here. But you know that actually the cyclist is moving at a speed of v, but angular speed is not that useful here. So let's forget about this alternative. The first one is better. mv squared over r. The next step is how to substitute fs. In general, we don't have any solution for that, but in a special case, we do. Let's say Fs is mv squared over r. Mass of the cyclist is constant, and let's say the radius of this roundabout also is constant. What about the speed? I'm not confident. You may increase the speed. The faster you go, the more static friction you need to hold you on this circular path. But when you increase the velocity, the speed, finally you will get the maximum static friction. You know the maximum static friction, Fs max, is going to be mu s, static friction coefficient, times the normal force. And here the normal force is going to be equal to mg. Because vertically the cyclist has no acceleration. So instead of n, I can put mg. Okay, so we have already raised the velocity, raised the speed to maximum speed, let's say it's V max, and so Fs can be substituted here for mu s mg. This is a very special case, the maximum safe speed, okay? So in general, there is no any more solution for that, but in a special, when you are in at maximum speed, yes. So this formula is just correct when the speed of the cyclist is maximum safe speed to avoid sliding on the ground. Okay, let's drop the mass from both sides and then you will find the maximum safe speed to be square root of mu s rg. Mu s is the coefficient of static friction, r is the radius of the roundabout, and g is the gravitational acceleration. Look at this one, a similar case on a turntable. A small box is placed at the edge of the turntable of radius 30 centimeters IUC that rotates about the vertical axis. Okay, so the rotation is horizontal and the object is here. Okay, the coefficient of static friction between the box and the turntable is 0.7. So basically the problem has already assumed that the object is at rest relative to the turntable. Determine the maximum angular speed of the turntable so that the box does not fall off. Okay, let me consider the case from the scratch. You know that there is a downward force of mg and a normal force canceling that, which is going to be equal to mg. And you might have you must have actually a force accepting the uh, responsibility of centripetal force. Here again, the static friction. Why static friction? Because the object is relatively at rest to the turntable. So let's start with Fs equals mv square over r. But it's not a good alternative. Why? Because the question is looking for maximum angular speed. So let's take r omega square. It's the better alternative. Okay. The next step after we take it to be Fs is the special case. Maximum angular speed is that. Here you have a constant radius, you have a constant mass for the object, but you can increase the omega. So Fs is going to be increased to the maximum. Maximum Fs is going to be mu s mg, as I explained in previous problem. So here you are in maximum omega. And so if you are going to find the maximum angular speed, you have to substitute Fs for mu s mg. Let's do it like that. And then I can again drop m and then find the omega max to be square of mu sg divided by r. Here the coefficient of static friction is given to be 0.7. Let's take the gravitational acceleration to be 9.8 and it's divided by 0.3. Here is the radius of the circle converted to SI units. And finally, the omega is going to be 4.7 radians per second. Maximum safe omega to avoid the object to fall off. Rotor is a very interesting instrument in amusement parks. People stand inside the wall of this huge cylinder. The cylinder at the beginning has a base, so people can stand here. But as the rotor speeds up and the rotation is getting faster and faster, people will experience a very large normal force. So it can generate a very big friction force, canceling the weight. So if they take the bottom off, people can easily stick to the walls of this huge cylinder. It's very exciting. Let's consider the physics behind that. Here, this is the cylinder, and let's take the radius of the cylinder to be r, and the rotation is horizontal. Here is the person or the object stuck tightly to that cylinder and won't drop. Why it won't drop? Because there is mg downward, but static friction hopefully cancels that. Actually, static friction is used here, not kinetic friction. The reason, because the static friction is used in the cases that the object is not sliding on the other, and it is here. Think about the person here inside the cylinder. The person has no relative motion to the cylinder. He or she will stick to the cylinder, so the static friction is useful here. So Fs is going to be equal to mg. So vertically, we should cancel the mg by Fs to confirm the vertical stability. Vertical stability means that there is no vertical acceleration. Newton's first law. But on horizontal direction, actually there is a normal force, but it won't be cancelled by something. So the normal force is gonna supply the centripetal force. So here I can write normal force to be mr omega square. This is the Newton's second law. So here Fc is going to be normal force. Okay? Now let's consider this problem. Find the minimum angular speed for an object in a rotor with radius r and a static friction coefficient of mu s. It's a parametric question. Okay, I told you normal force is going to be mr omega square. And vertically, Fs is cancelling mg. They are looking for minimum angular speed. Why minimum angular speed? You know that we need a minimum normal force to be able to supply enough static friction to cancel the mg. Okay, less than that, the object will fall. So minimum normal force means minimum omega, and it's exactly looking for that. So when I say minimum normal force, I'm confirming that Fs is in threshold of motion. In threshold of motion, we are allowed to use mu s times normal force. So when I use this one, I'm confirming the instability of the case. Less than that, the normal force is not enough, and mu s times n will not cancel mg. What happens next? The object will fall. Hopefully it won't in amusing part. Okay, let's continue. Here I substitute n for mr omega squared here, and then the minimum omega, you know that here we have implicitly suppose that it's the minimum omega. Less than that, normal force is not enough. So minimum omega is going to be square of g over mu s r. Less than that, it's not safe to use this rotor. Banking of the road. In mountain roads or race, it's very usual to give a transverse slope to the road to make safe driving. But why? First of all, let's consider the free body diagram for this vehicle. Actually, there are two forces acting on that and not more because we ignore the friction. I ignore the friction here because of reducing the complexity of the question. Actually, including the friction will make the problem very complex. So let's have just downward mg, and the other is the normal force. I'm sure that you confirm there is no any other force if we ignore the friction. So let's now consider the case in circular motion. Don't forget that there is a circular path like that. So the center of the circle is here. I need a centripetal force, and better than that, a force to supply the centripetal force to keep and guarantee this horizontal circular path. What is that force? We should decompose the normal force to find it. It's very easy to check. The legs of this angle are 1-to-1 perpendicular to the legs of this angle. So these two angles have the same measure. So it's also theta. They are congruent. Okay? Now, n can be decomposed like that. The horizontal is going to be n sine of theta. It's very easy because if I make a right triangle here, let's say this horizontal side is nx, okay? Here, sine of theta is going to be nx, the opposite divided by the hypotenuse n. So nx seems to be n sine of theta. This is the horizontal component of that normal force. And as the center of the circle is here, this horizontal force will guarantee and supply the centripetal force. mr omega square or mv square over r. Which one do you prefer? Yeah, the second one. Actually, the first one is not that applicable here because we always in problems like a vehicle and so forth, consider the speed of the object, not the angular speed. Okay, so here I can say it's n sine of theta equals mv squared over r. This is the Newton's second law. And what about the vertical side? In vertical side, actually the vehicle is at rest. In vertical direction, there is no acceleration. And so here, n cosine of theta, the vertical component of n, will cancel the mg. Let's write it here. So this is going to be the Newton's first law in vertical direction. I'm going to get rid of normal force. So I can divide both sides of these equations one by one. If I divide these two, sine over cosine is going to be tangent of theta. And if I divide these two sides, I can drop them m, and here I will get v squared divided by rg. This is the final result. Tangent of theta v squared over rg. Tangent of theta is the slope of this bank. Okay? It's very interesting that it's totally independent of mg, independent of m actually. Mass of the vehicle and the object is not important in this case. And don't forget, here basically we have already supposed that there is no friction. Including friction will increase the complexity of the question, and it's out of discussion for the time being. Commercial airline pilots fly around a banked curve to change the direction of the passenger jet. When the angle is correct, the passengers will not feel the turn, and you may have experienced that in flight. They just feel a marginal increase in weight. You know the reason, because this marginal increase is because of the normal force. Actually, it's larger than mg, and when the airplane is horizontal, let's say here the airplane is horizontal, okay, passengers feels a normal force equal to mg, okay, well you can easily show that here the normal force is larger than mg. The reason I will tell you, because I told you in previous page we had it, and sine and cosine of theta is mg, so because of that n is gonna be mg divided by cosine of theta. As cosine of theta is something always less than 1, so this fraction is larger than mg. So normal force in this case is going to be larger than mg. So the passengers will feel a marginal increase in weight, but it's not going to affect their comfort. Some high-speed trains also have this uh, get advantage of this technology, tilt as they go around curves so that the passengers feel more comfortable. Here again they use the same transverse slope banking, and so normal force may be slightly larger than mg, but it gives a lot of comfort to passengers. Let's consider this problem. An aircraft flying at a constant speed makes a banked turn in a horizontal plane. The wings of the aircraft make an angle of theta with the horizontal. Draw the free body diagram showing the forces acting on the aircraft in the vertical plane. Okay, I told you there are just two forces acting on this object because we ignore the friction. First is the lift force here because it's playing the role of the normal force, same as the normal force, and the other is downward force of mg weight. That's all. These are the two forces you should draw in free body diagram. But it's also very considerable that you should show that F, lift force, is slightly larger than W. The reason, because a component of F, the vertical component of F, let's say is Fy, can cancel the W. So F must be larger than W to supply this vertical canceling component. Okay, this is the resultant force. It's not necessary in the free body diagram. I'm just showing the resultant force here. This is the resultant force of F and W. And if you are, as a pilot, you are going to have a horizontal circle. This horizontal resultant force must be really, really horizontal. Uh, Otherwise, if it's tilted up or down, the airplane, rather than the horizontal circular path, it may deviate upward or downward. The part B of the question, the speed of the aircraft is given to be 180 meters per second, and the radius of the turn is 7,400 meters. Determine the banking angle of theta. It's very easy. You can easily show that this is the banking, the theta, and legs of this angle 1 to 1 are perpendicular to this bank. Okay, so we can easily take these two angles to be congruent. Now we can continue exactly based on the first approach I explained. So let's use it directly to be tangent of theta to be v squared over rg. R is the radius of this circle, and it's given here 7,400 meters. V is the speed of the aircraft. Unfortunately, it's in SI units, and that's nothing unclear. We have everything. So the answer is going to be 0.447. But this is the tangent of theta, and if you are going to have the banking angle, you have to use tangent inverse function in your calculator and find the theta to be 24 degrees. Okay. The second category of the problems we are going to consider are the ones in which the object is moving in vertical circle. What do I mean by the vertical circle? One of them is moving a car on a convex bridge. Look at this bridge. It's of course very hypothetical. Bridges are not like that, very spherical or circular like this, but let's say it's very idealized. And the car is at the top of this bridge, okay, moving at speed of v. What are the forces acting on this car? First of all, you will consider the car in a circular path, and the center of this circle is here. So there must be a centripetal force. I'm sure that you agree. A centripetal force to the center to hold the object in this vertical circular path. But this FC is not that easy. The reason, because in vertical direction there are two forces acting on this car. What are those forces? Yes, one of them downward force of mg and the other is the normal force. This is a very common mistake among students. They think that normal force will cancel the mg, but it's very big mistake. Normal force can never cancel mg. Why? Because if they cancel each other, vertically the car is actually not accelerated. And so how can you have a downward acceleration of centripetal force? It's crazy. The object will not go on this. So the car will fly in the air horizontally. You must have larger mg and a smaller n to make a resultant force downward to use it as this centripetal force. So keep in mind that mg here is larger than n. And if you are going to draw the free body diagram, ignoring friction, these two forces are the only ones you should draw, and mg larger. Okay, so if the radius is r, here I can write mg minus n, necessarily mg is larger, I told you, is going to be mv square over r. In this case, as we are always involved with the speed, I prefer mv square over r rather than mr omega square. The other is when the car is moving on a concave bridge. Instead of convex one, it's the concave one. It's of course very hypothetical. I told you the bridge is not going to be like this, but let's hypothesize that and learn it. What are the forces acting on this car ignoring friction? Yes, again mg and n. But here, normal force is larger. Why? Because the center of the circle is here and the car is here at the bottom part. Okay? The object must be acted by a resultant force of Fc to the center. Otherwise, it won't have this acceleration and cannot keep circular path. So normal force is necessarily larger than mg. Okay, so here I can write n minus mg to be mv square over r. You see that when the object is moving in vertical circle, here we are faced with a more complex case in which Fc is a combination of two forces. Look at this problem. It's just a numerical one. A car is traveling on a convex bridge of radius r. Okay, show that the car will lose its contact with the bridge if the speed is larger than this. It's an action movie. Square of gr. Okay, think about it. What do they mean when they say the car will lose its contact? Lose its contact means there is no normal force. Think about it. You are driving a car or a bicycle on a horizontal road, okay? You are acted by a normal force and also a downward force of mg. Forget about the forward force or friction. Okay, basically normal force will guarantee that you are in touch with the ground. Suppose that a crane is lifting you up. After a while, you will lose your contact with the ground. That's all. When you lose your contact, basically there is no normal force because normal force is due to the contact of the vehicle with the horizontal or let's say the road, the ground. So here when they say it will lose the contact, it means that there is no normal force. Okay, so there is just mg. Forget about normal force. The reason is that the speed is so high that then there is no need for normal force. mg will supply the whole Fc. So here I have, in general I have n, but I will ignore it. So here I will write mg minus n in general to be mv square over r, and then let's drop the n. So mg is going to be mv square over r. If I drop the mass, across the mass from both sides, I will have maximum speed to be square of gr. This is the minimum speed. This is the minimum speed you need for the car to lose its contact with the bridge. Faster than that, it's okay. It will fly and will be a real action movie. Less than that, you still have your contact. Now let's consider pendulum. It's a very interesting case. It's also a vertical circular path. Let's say the pendulum is swinging and it's the dead point, okay? Actually, here the speed of the pendulum is gonna be zero and it goes back, okay? And you know that it will go to the same altitude on the right side and then it stops again. So there is another dead point here at zero speed and then goes back. It will have the maximum speed when it's moving uh, through the vertical position. Maximum speed, you know. Okay, let's start it from the left dead point. Here, the forces acting on this bob in this pendulum, ignoring the weight of the rope, are mg, and the other is the tension. T1 is the tension of the rope at this point. These are the two forces acting on the bob. Let's say the mass of the bob is m. Okay, that's all. But you may have a question. Is the T1 larger or smaller than mg? I will tell you the answer. Okay. Here, you should first consider this direction. Is the object accelerating on this direction or no? The answer is no. You're right. Okay, why? Because let's say the angle of deviation is theta here. This is vertical and this is vertical and this is an oblique, so it must be a congruent angle. So it's also theta. And the component of mg on this direction is going to be mg cosine of theta, okay? This component of mg will be cancelled by t1 because in this direction, the bob is not accelerating, okay? So if t1 is equal to mg cosine of theta, immediately I can conclude that t1 is, let's say t1 is smaller than mg because cosine of theta is something always less than 1. So t1 is less than mg. And so if you are going to draw a free body diagram for the bob at this point, you will draw a small t1 and a larger downward mg. Okay, this is for this dead point. I will again remind you something. At this point, as I told you, there is no speed. So although it's part of a circular path, but at this point, the object has no speed. So you don't have to consider any centripetal force. I know that the center of the circle is here, but there is no centripetal force because it's not actually moving on this circular path. What about here, at the bottom point? When the object is passing through the vertical position, it is highly affected by the centripetal force. Why? Because it's moving at a very high speed. So if you ignore the centripetal force, you should forget about circular path. At this point, so we will have a downward mg and a very large T2. Why the tension of the rope is very large and larger than mg? Because you need a centered resultant force to supply the centripetal force, Fc. So T2 is larger than mg. Okay, for sure. How to write Fc? Fc is equal to the vertical resultant force. Considering the center of the circle here, Fc is going to be T2 minus mg. So I can easily write T2 to be mg plus mv squared over r. This is exactly the Fc. Okay? What about a point in between? Not to be at the bottom point and not to be at the dead point. Like this. What can I do here? Okay, it's not that complicated. You can again consider an mg and a T3. T3 is the tension of the rope at this point. You may have a question again, which one is larger, T3 and or mg? I will tell you the answer. Just again consider a deviation like alpha here. Let's take it to be alpha, okay? And so accordingly, it's also congruent angle of alpha. And here you will have mg cosine of alpha, okay? T3 is larger than mg cosine. It must be larger because it's moving at this point. And as you have a speed, you need a centripetal force. So the resultant force is to the center. Based on that, T3 is larger than mg cosine of theta. So I can write T3 minus mg cosine of alpha to be equal to mv squared over r. And r is actually L, the length of this pendulum, and v is the speed of the pendulum at this point. Okay, so let's write it in this way, and T3 comes out like mg cosine of alpha plus mv squared over L. But in principle, T3 can be larger than mg or smaller than mg. It depends on the point. There are some points, just a specific point at which T3 is equal to mg at this point, maybe, and after that is larger, before that is smaller. Okay, I don't know, it depends. It depends on a lot of things. Think about it. It's v squared, changing factor, so this term is highly affected by speed, and also alpha is also variable. So these two terms both have something to change. Based on the mixture of them and considering conservation of energy, you can find the point at which T3 is equal to mg. So after that, deviating to the center, T3 is going to be larger, before that, smaller. Okay, find it as a very good practice, I think. Let's consider pendulum in full circular motion. Okay, let's say the pendulum is so fast that it can go round the circle in a vertical, complete circular path. Okay, at the bottom point, you see TA, let's say it's the point A. As the object has a maximum speed, TA is very large and mg not that big. You know why TA must be larger than mg, because the centripetal force is always the resultant force to the center. So TA is larger than mg. Here I will write TA minus mg to be mv squared over L at the point A, the bottom point. In horizontal position B and D, actually mg is downward. Okay, mg is a vector downward, so it doesn't have any direct effect on the centripetal force. Forget about mg. So this is just the tension of the rope, to be equal, of course, in both B and D points, to supply the Fc. So I can write Tb equal to Td to be mv squared divided by L. And by conservation of energy, we know that D and B will have the same speeds. At the top point, here actually the object is acted again by in principle, a couple of forces, mg and Tc. mg necessarily exists because it's moving in gravity, but Tc depends. Anyway, let's say it's fast enough to have also a tension. Here again, the resultant force, fortunately, is evident, is to the center. So Tc plus mg, the total resultant force, is going to be mv squared divided by L. But I will tell you something here. Look at this term. The first term, actually Tc, may be zero. What do I mean by that? If you reduce the Vc, the right side of this equation will drop. And so if it is small enough to be equal to mg, there is no need to have a Tc. So if I ignore the Tc in a very critical situation, mg seems to be equal to mv squared over L at the point C. So if I drop the mass, v is gonna be square of gl. This is the minimum speed at the top point to keep the rope stretched. Otherwise, it will, if it's slower than that, the weight of the bob will cramp the string and it's not gonna have a complete circular path. Anyway, here I can write it as here and at the bottom point to be the maximum tension. The reason, because at the bottom point, the object has maximum speed, and as you see, TA seems to be mg plus mv squared over L. Here mg is added up to Fc, mv squared over L, and more than that, v is maximum. So at the bottom point, the object necessarily will experience the maximum tension at the top, minimum tension, and that minimum I told you sometimes can be zero. The minimum speed for having that seems to be square of GL, as I explained. Thank you very much for being with me and watching this video. Please watch the video again. If you have some challenges, ask your questions in comments. I will answer them very quickly, and also share your valuable opinions with me to improve the quality of these videos. Thank you. See you.